Hi everyone, today's lesson is on medians, altitudes, perpendicular bisectors. A little bit of review and then some proofs. So let's get started. First thing I want to do is do a little bit of a vocabulary review. The converse of something is basically based on if you have a statement, whether a hypothesis and a conclusion, right? You have your conditional. The converse is when you're taking your conditional and you're taking your hypothesis and your conclusion and you're flipping it. And so that's then the hypothesis is now the conclusion is now the hypothesis. Perpendicular basically means that you have two lines that come together to form a right angle. Vertex is a corner of your triangle where your two endpoints meet. The midpoint is the middle point here where you have this number. If this is the midpoint, then this segment here is congruent to that segment there. Congruent meaning same size, same shape. Equidistant means same distance away. Reflexive property, you use that when you're trying to say maybe segment AB is congruent to itself. You can also say angle A is congruent to angle A. A lot of times people use the reflexive property when maybe they're trying to prove two triangles are congruent. And you have this one line in between the two triangles, so that if you did this and you split them up and you took this triangle here and you moved it out, that edge right here would be the same as that edge right here. And so from that triangle, so you could separate them, and this middle line would be the same. Isosceles triangle is a triangle that has two equal sides. So if you have two equal sides, then it's an isosceles triangle. The converse of the isosceles triangle theorem, which we call ITT, would mean that if I have, the isosceles triangle theorem says that if I have two sides that are congruent, then their opposite angles are congruent. The converse, there's our new word, the converse says if my two angles are congruent, then my two sides are congruent. Equilateral triangle is where you have three sides congruent in a triangle. Likewise, you could have an equiangular triangle, because if the sides are congruent, then the opposite sides, the opposite angles are also congruent. SAS stands for side angle side. So if you have a side congruent in two triangles, if you have a side congruent to another side, an angle, notice how it's in between, an angle is congruent to an angle, and then another side congruent to another side, that's side angle side. Likewise, you could have angle angle side, side side side, hypotenuse leg, angle side angle, and then CPCTC stands for corresponding parts of congruent triangles are congruent, because once you've proven that the two triangles are congruent by one of these methods right here, then all of their parts are congruent. So you could say all the parts are congruent once the two triangles are congruent. So based on all of that information, we're going to attempt this proof. So if I were you, I would pause the video and then put in all your information and then try to solve it and then come back to it. So assuming you did that, we're going to put in angle 1 is congruent to angle 2. And we also know that that's congruent to angle 3 here. So a couple of things right off the bat that I'm thinking is if I have two angles congruent in a triangle, that makes it an isosceles triangle. It also would mean, in one of my steps, I could say that this segment is congruent to this segment, right? Because the side's opposite of congruent angles, that's the converse of the isosceles triangle theorem. Additionally, we know that EN, so we know that this whole length right here is congruent to this whole length right here, okay? So let's see where that puts us. We know that, let's see here, and what I'm trying to prove is angle 4 is congruent to angle 5. So what I'm looking at right now is I'm looking at angle 4 in this triangle right here, okay? So I want you to look at this triangle right here, all right? And then we have a different angle, and I'm looking at this triangle right here, okay, is what I'm seeing. I don't know if you're seeing that, but that's what I see. And just keeping in mind, if I were to move those two triangles apart, right? Oops, not that one. If I were to move those two triangles apart, right, I know that this angle, which is angle 4, is congruent to this angle, which is angle 5, right? We also know that EN, this segment here, is congruent to DG, which is this segment here. Now, remember, you need 3 parts of one triangle to prove it congruent to another triangle. So something has to do with these angles being congruent, because based on if the angles are congruent, then the sides are congruent, right? So therefore, CEM is D equal to DM. So I know that EM, which is this side here, is congruent to DM, which is this side. Now that is not helpful because that's that side-side angle, which is not what I want. But we do know what we can say is if this angle is congruent to this angle. So let me put this back for just a second so I can see that. It looks like that angle, right, also, if that's angle 4, we also know that this angle E right here is congruent to angle 3, and let's talk about that. So put that all together in your head and then take a minute, and you're looking at EM congruent to DM. What would that reason be? Why would these two triangles be congruent? And then why would then the angles be congruent? Okay, so hopefully what you did was you went through this and you realized that this was based on the isosceles triangle theorem, but the converse, because if the angles are congruent, then the sides are congruent. We know that these two triangles are congruent. We could say by side angle side. Additionally, we could say then that angle 4 is congruent to angle 5, which is what we want to prove, and that's done by CPCTC. So the next proof is this one, and again, same thing. I would pause the video and I would try to work some of this out on your own and then come back to it. So I'm assuming that you paused the video and you're back, so let's put in what we know. We know that angle 1 is congruent to angle 2. We know that angle 3, this angle, is congruent to angle 4. And that's given. So you would just say given, and then you would state the given, which is angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4. Then you also know that SV is actually congruent to itself. So we can say that SV is congruent to itself by the reflexive property. And the reason I would want to do that is to prove that these triangles here are congruent. Now, you need to ask yourself what you're actually trying to prove. Well, you're trying to prove that this line right here, TU, is congruent to TW. Okay, so based on that right there, if I prove these two triangles congruent, I can then say that this side is congruent to this side here, right? And then additionally, we can say we know that this segment here is congruent to itself, and that would be by the reflexive property. And then we would need to think about how we can say, like, angle-wise, how can we prove that the angles are congruent, etc. So I'm getting to that, but that's like a step. So write your thoughts down, and hopefully what you've done is you've come to something like this, where we've said just this, SV is congruent to SV. That was my reflexive property, okay? We know that SVU, we know that that's congruent to the other one because remember, this was an angle congruent to an angle. We had another angle here congruent to another angle here, and then we had this side congruent to itself. So that was angle side angle. Okay, so then we can say parts are congruent by CPCTC, which I would say US is congruent to WS, and so we would say that by CPCTC. Then I would say TV. Now I'm thinking this whole triangle is congruent. See, now this is what we're looking at here. See, a lot of us were looking at just this little part here, but in reality, I want the whole triangle. Okay, because what that means is me saying US is congruent to itself, or US is congruent to SU or SW. That's not part of what I need. What I need is this whole triangle. So if you wrote this, okay, we're going to erase that, and we're going to say UV is congruent to, WV, okay, you see that? Because then you can say this is congruent to this. You already know that this angle here, 3, is congruent to angle 4, and if you say TV, like what we said here, is congruent to itself by the reflexive property, then this big triangle is congruent by side angle side. There you go. And so you can say angle TUV is congruent to angle TWV. And therefore TU is congruent to TW by CPCTC. So be careful, because there's different ways to look at it. I mean, I suppose that we could have done it this way too, but we would have had to have done some sort of thing with a linear pair and saying that these angles plus each other, this angle plus this one is equal to this angle plus this angle. That would have been this angle congruent to that angle, and then I would also have had it congruent by side angle side. So another option, I could have done that. Okay. So today's lesson is all about the different parts of a triangle, but also different segments that can be found in or out of a triangle. So what we're looking at is called the angle bisector. And, you know, an angle bisector is a segment or ray that bisects an angle. It divides it into 2 equal parts. Okay? You can have 3 different angle bisectors in a triangle. So if I had a triangle like this, and let's say that I bisected this angle right here, where that equals that, and then I bisected this angle right here, where this angle is congruent to that angle, and then I bisected this angle here, right, where those were equal or congruent, I would actually have this point in the middle, and that point in the middle where all 3, if I had 3 angle bisectors in one triangle, would be called the incenter, okay? And what's cool about the incenter is actually, if I had a compass, I could put my point right here and my pencil here on one side, and I would be able to draw a circle, a perfect circle in the inside of this triangle using this incenter, which is the result of 3 angle bisectors. Okay, additionally, you can have, let's see, we have a perpendicular bisector in a triangle. Now, a perpendicular bisector does not have to originate at the vertex, but because what it does is it's this very large line, long line, okay, that does this, and it bisects a side, and it's also perpendicular when it does that. So I could actually bisect 3 sides within a triangle, okay, 3 perpendicular bisectors, right? And what would happen is I would then get something right here, another bisector, see that? And I would get this point here in the middle, 3 perpendicular bisectors, 3 of them, okay, 3 perpendicular bisectors gives me something called the circumcenter. Okay, and like 3 angle bisectors, which gives me the incenter, the circumcenter allows me to put my compass on this point of intersection and go to, not to a side, but go to an actual corner. And I would be able to draw, if I had a compass, would be a lot better, a circle around, and it would actually touch each of my vertices, just like that. That's called circumscribing my triangle. This button right here, that point of intersection, is called the circumcenter. An altitude measures the height of the triangle, and it comes down, straight down. It is perpendicular. It doesn't necessarily divide this into 2 equal parts, right? What it does is it just comes down from the vertex, where the other one, just the incenter, the angle bisector came from the vertex, but the perpendicular bisector does not have to. But this comes straight down and it measures the height. So that's called my altitude. Okay, now keep in mind that if my triangle looked something like this, okay, my altitude if I extended my side, because it does measure the height, would come straight down like that, and that would be the length of my altitude. And like the other two triangles that we just did, if I had 3 altitudes, okay, if I had 3 of those, what it would do is it would actually also come together into a point, and that point of intersection is called the orthocenter. Okay? You can't draw any cool triangle or circles around that, but that's what an altitude does. That's what 3 altitudes do. Additionally, we have something called a median. Now, a median connects the vertex, okay, connects the vertex with the midpoint. And that's really important because you had to have had a perpendicular bisector happen first in order to get this midpoint, to get from here to the midpoint, okay? So like all the other triangles that we talked about, this is called a median, okay? And if I had 3 perpendicular bisectors, okay, I'm just going to draw the perpendicular bisectors in first, right? And we already know that they meet already together, but that's not the point of what I'm doing here. If I have from this vertex and I connect to that, right, to that perpendicular bisector, which is the median, we'll see how these equal that, and then I connect this vertex to this perpendicular bisector, okay, try to get that straight and having a little difficulty. These are 3 medians, so 3 medians give me what's called this point of intersection here, which is called the centroid. And the centroid is another name for it is the center of mass, meaning I could probably balance my triangle on the center of mass like that. And anyway, and it would be completely balanced. So of the 3, again, we have the median, and the median connects from my vertex to the perpendicular bisector, which gives me the midpoint. Okay? So this is my green line right here. That's my median. Okay? Now, this purple line right here, that's my perpendicular bisector right here. That's my perpendicular bisector. This blue line right here, see the angle that it bisects? That's my angle bisector. And the red line, because it comes straight down and it measures the height, we call that the altitude. And so those are the 4 things that you will need to know for your test. And those are all about the points of intersection as well, and you need to know those too. So again, 4 types of special segments in triangles. We have we're going to call medians, altitudes, angle bisectors, and perpendicular bisectors. So again, 3 medians is going to give me my centroid, okay, which is the center of mass. 3 altitudes is going to give me my orthocenter. 3 angle bisectors is going to give me my incenter. And 3 perpendicular bisectors are going to give me my circumcenter. And remember, only 2 of these, the incenter, I can also draw a circle inside, okay? And we call that the inscribing a circle. And then the circumcenter is something that I can call, that's where you have the center and you draw a circle. The inside one was inside to the sides, and the perpendicular bisector is a circle inside. Well, you put the sharp part of your compass on the point of intersection. I believe it could be outside, and then you draw your circle from the center to each vertex or vertice. Okay, and that's called circumscribing. Okay, so looking at this, we've got a median. We have 3 medians, and these are the different ways you can draw a median. So you're going to draw a median vertex to the midpoint, vertex to the midpoint, vertex to the midpoint. If I had put all of these in the same triangle, this is what it would be, and I would have this point right here of intersection, and that point of intersection is called the centroid. And then that's basically found by making a segment from a vertex to the midpoint of the opposite side. Point of concurrency, 3 or more lines or segments intersect, and that's the intersection point. There's a fancy name for that. It's called the point of concurrency. In this, for the median, the point of concurrency, like we talked about, this point of concurrency is called the centroid. Okay, center of mass. For an altitude, it's the perpendicular segment from any vertex to a line opposite. Now, that does not have to be inside the triangle. Like I said before, you could have a triangle that looks like this, and then your altitude is actually outside of the triangle. So keep that in mind. 3 altitudes are all altitude of a triangle. These altitudes are all inside of the triangle, but they're not always. Because if I had done this, and I had done my 3 altitudes this way, okay, there's 1 altitude, right? I'm going to extend my line. There's 1. This altitude here, okay, I extend that. That's not going to be inside. It's going to keep going outside. And then this one, I do have to extend this line, and then that altitude also. So this right here is my orthocenter, and that's 3 altitudes. And they do not have to intersect inside the triangle. They can intersect outside. In a right triangle, the altitudes are the legs of the triangle, okay? So you have, see this, there's my altitude, and then for this one, this would just be straight up and down like that. That's the altitude right there. And that would be that height of that triangle. In an obtuse triangle, 2 of the altitudes are outside of the triangle. See, there's this one right here, right? That's inside. We extended this. We just talked about this. See, extend that down, extend that down, extend that down. There, right there, is my orthocenter. And the point of concurrency for the altitude, again, is called the orthocenter. In an acute triangle, it's going to be inside. But, of course, for an obtuse triangle, your orthocenter will be outside of the triangle. So an angle bisector is a line or ray segment from the vertex that cuts the angle into 2 congruent parts. So I think this one is the easiest one that most students really like this one. That's congruent to that. That's congruent to that. And then you've got this one where this angle here is congruent to that angle here. Again, they do intersect in the center. I can draw, that point of intersection is called the in-center. And I also can draw, or inscribe a circle inside if I chose to. Something that we're going to learn in the constructions chapter future on. The point of congruency for an angle bisector is called the in-center, which is this point right here. That's the in-center. This circle right here is inscribing. That's an inscribed, we'll call it an inscribed circle. Okay? Then we have the last one is called a perpendicular bisector. The perpendicular bisector is something that you can do with a the medians, right? Because if this had been a median, I could connect this point to the midpoint, right? That would be a median. Okay, so while I'm drawing my medians, I'm also drawing my perpendicular bisectors. But anyway, for this, it's also, the main 2 things is it is perpendicular and you are bisecting each side. And you can do that 3 times all the way around. The point of concurrency is called a circumcenter. And of course, if I had put my center here on my compass and I went to a corner, I feel like I should be able to do that. I don't remember. I feel like this is something, let's see. I know there's my compass. Let's see how, if we could actually make this work. Let me see if I can move this. There's the point. Let's see. It's been a while since I've done this, but let's see if this will work here. Move that out to a corner. Let's see. Kind of. Maybe move it up a little bit. There we go. And let's see. If I were to swing it around, let's see what would happen. There we go. So cool. Anyway, that's what we will be doing once we get to the construction chapter. But that's what I'm talking about, and that's what we call circumscribing a circle. That's called you're taking your circumcenter and you're going circumscribing. Whoops. Okay, a circle. So again, these are matching perpendicular bisectors. 3 perpendicular bisectors give me, let's see, a midpoint. Is this a matching? Maybe not. Okay, maybe I'll just draw a line. Oh, there it goes. Congruent angles, those go with my angle bisectors. Perpendicular bisectors go here. Medians do connect to a midpoint, but also perpendicular bisectors are perpendicular and they do bisect, making a midpoint. Congruent segments, that would be giving me perpendicular bisectors. Perpendicular bisectors, although I do need a perpendicular bisector in order to make a median. Medians do give me my midpoint. Congruent segments, this one really didn't talk about. This is also perpendicular, whether it's inside or outside of the triangle. So I guess I could have used this one for that also. Congruent segments is perpendicular bisector as well. So name each of the following segments. So the median of angle ABC, ABC would be connecting to the midpoint. So here's A, B, C. The median would connect to the midpoint. So it'd be from here to here. So that would be CF. CF. I believe that it could also be BE. Okay, that could also be BE. The altitude of ABC would be AD. The bisector of an angle would be CF. Yep. In your packets, you would turn to page 8, and you would create this here. Sketch each median from each vertex of triangle ABC. So the median, once I have a perpendicular bisector, my median would go from here to here. For this one, once I have my perpendicular bisector, my median would go from here to here. And once I had my perpendicular bisector, my median would go from here to here. For this one, sketch each altitude. This would go straight down. This one, depending, sketch. So we're going to say it's about there. And lastly, let's see, if this is a right triangle, I'm not sure if it is. It kind of looks like it, but we're not sure. We'll just do that. Sketch each altitude. Well, these are already done except for this one, which would be that altitude. And lastly, the altitude for the last 3 problems would be, there's one altitude, if I extend that. There's this altitude, if I extend that. And if I extend this line, I would have that altitude right there. So now you have an altitude from 3 different types of triangles. And check your work. And a couple of challenging scenarios. So what is the distance from your right foot to the water? Well, the distance from your right foot to your water, if you think about it, here's my right foot, or right foot, depending on which side I'm on, would be straight down, wouldn't you say? So technically, the distance between a point and a line is defined as the length of the perpendicular segment. It's always going to be the straightest line segment there. So it's always going to be a straight line segment to the water, or to wherever you're trying to go, and it's going to be perpendicular. So what path should you take to swim away from the shark so that both sharks stay equally as far away from you as your right foot? So assume the sharks are going to stay still. I'm hoping that you don't go either to the right or to the left, but you actually go straight up. So if a point lies on the perpendicular bisector of a segment, so anytime it's a point here, then it is equidistant from the endpoint. See, from here to here, it's going to be the same distance. As I move along this, from here to here, right? As I move along, it's going to keep staying. That distance is going to stay the same all the way up. Suppose 2 kids are swimming at the same rate on the pass. Along what path should you swim? Well, to stay equidistant from each kid, again, perpendicular distance straight up and down is what I would do. And if a point lies on this angle bisector, okay, perpendicular here, then it is equidistant from each of the sides of the triangle. So basically, as you're swimming, right, it's going to be the same distance on both sides of the triangle from here to here. So a couple of postulates. The distance between a point and a line is defined as the length of the perpendicular segment. The theorem states if a point lies on the angle bisector, so you have an angle bisector, so there's my angle, here's my angle bisector. If a point lies on the angle bisector anywhere, then it is equidistant from both sides. Okay, do you see that? It'll be equidistant from both sides every time. And the converse is always going to be true. Keep in mind that that distance, okay, this distance from here to here, okay, can be this perpendicular, 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 etc. The point on the perpendicular bisector theorem, if a point lies on the perpendicular bisector of a segment, the point is equidistant from each of the endpoints. So again, this is another one of those things that as I go along this perpendicular line right here, every time B and C, it's going to be the same distance each time I move up and down that line, okay? There is a perpendicular, there is the proof for perpendicular bisector. And this is something that you should pause your computer and work through this, and to prove that AB, this length here, your ultimate goal is to prove this is congruent to this right here. Okay, you do know that this is the perpendicular bisector, and given that this is the perpendicular bisector, a couple of things are happening. Okay, number one, you know that this is perpendicular, they form congruent right angles. Okay, number two, if it's a perpendicular, this word, bisector, that means it does cut this into two equal parts. You could also say that AX is congruent to itself. So you're going to prove that these two triangles here are congruent by side angle side, and therefore the parts are going to be congruent. So I would go through that and try to make sure that you have each of those steps written out. Here are the steps, but the actual proof to check your answers is right here, and I do hope that you spend some time on that, doing that. So pause the video, check your work. Just a couple of things that I do want to point out is when I say something is a perpendicular bisector, okay, and you know in your mind you're thinking, oh, well that means that this is going to bisect it, so that's congruent to that, right? That's just the definition of bisector. But see this right here where it says it's perpendicular? You can't just automatically say that that angle is congruent to this angle here. Even though you know that they're both right angles, you have to say the whole gambit there. You have to say, number one, that it's a right angle. Number two, you have to state that right angles have a measure of 90 degrees. And then, therefore, if these two are measures of the same right here, right, then I can say this angle is congruent to this. So there is a process for saying, just for somebody saying, hey, there's the perpendicular bisector. That actually always comes with, 3 to 4 steps where you have to, say that the angles are congruent. And that their measures are 90, therefore they are congruent by substitution. Some people say transitive, I prefer substitution. Then I can say AX is congruent to itself. You have side angle side, and then the two triangles are congruent. The parts are congruent once the angles are congruent. Okay? So true or false, the medians of a triangle always grow the inside of a triangle. That's going to be true, because the medians, being the centroid or the center of mass, always has to be inside of a triangle. The perpendicular bisectors always go through the inside, and that is not always true, because we can have this perpendicular bisector here. We have, well, actually it says they always go through the interior. At some point they do go through the interior, right? So you've got that happening, and then you've got this happening, but it doesn't necessarily mean that it didn't ask me for the circumcenter. It did say the bisector. So I would say they all do go through the inside. In a right triangle, two of the altitudes are also legs, yes. If a line is an altitude and a median, so if it's an altitude and a median, let's see, for it to be a median, this has to go to that, right? So for that to happen, I would actually need to have this be the median and the altitude. That would mean it's either an isosceles triangle, it would either mean it's an equilateral triangle. The median, it would have to also be the perpendicular bisector. So yes, that's true also. Keeping going, if a line is perpendicular bisector, if it's a perpendicular bisector and it's an altitude, okay, so then it has to be that's true. 3 medians and 3 altitudes intersect in the same point, a negative. If the perpendicular bisectors of the vertices of a triangle, then the triangle is acute. If they intersect the vertices of the triangle, then it is acute. So let's think about that. If this is an acute triangle and all my perpendicular bisectors are here, there's 1, there's 2, there's 3. If the perpendicular bisectors intersect the vertices of a triangle, then If the perpendicular bisectors intersect the vertices of the triangle, then the triangle is equilateral. So that would be true. Anyway, if time allows, there's some additional information that you can do. You can practice, and completing each statement. The answers are here. And that's all I have for you for today. Thanks for watching, and I'll see you soon.